my pleasure to introduce our first speaker of today's Eastern Hemisphere session, Ilia Gaiur from University of Birmingham, who will talk about extended duality for Calogero Painlevé and regional Painlevé systems.
Yeah, I want to thank again Anastasia, Nikita, and Beatrice for this event and for opportunity to talk here. So my talk will be about the duality arising in so-called Calogero Painlevé systems, which are already well known for community, and for some new Rusinars Painlevé systems. This work is a collaboration with Vladimir Rubtsov, so we have a preprint on archive, and also work is in progress. So the motivation for our work was the following kind of scheme. So we have a Painlevé systems which are kind of non-autonomous analogs of the integrable systems. Due to Manin and Levin and Alshanetsky, it's already known that this systems is just a deformation of two-particle Calogero module-like integrable systems, and this is called Painlevé-Calogero correspondence. For these systems, there is a quite obvious generalization for n-particle systems, and on the Painlevé side, we have some introduced by Takasaki multiparticle Painlevé systems, and the connection between these systems and multiparticle Inozemtsev systems was given 2 years ago by Bertola, Kafasa, and Rubtsov, and this correspondence uses Poisson reduction. The motivation for our work is that for these systems, for the classical and particle integrable systems, we have a dual systems which are quite well known and studied, and our target was to do the same on the side of the Painlevé equation. So we go from the dual systems in some sense here to the new non-autonomous systems here, which are dual to the multiparticle Painlevé systems. So I will start my talk with a review of the reduction of the multiparticle system from the different Hamiltonian G spaces. So as an example, I will consider the following phase space. This is T star to GLN, so it's just an GLN cross GLN with the following symplectic form, and the group, this group is GLN, obviously, acting on this space by just a diagonal conjugation of matrices P and Q, which are just coordinates in each direct indirect product of GLN. We know that this space is Hamiltonian G space, and the moment map, which sends every point of our phase space to the co-algebra to GLN star, is just a commutator of P and Q. So it's in some coadjoint orbit of the Lie group action. Now, to derive some integrable system from this picture, we should take some invariant Hamiltonian. Then, since Hamiltonian is invariant, the moment map is the constant of motion, and we can do a reduction. We take a simplest possible Hamiltonian, I guess. This is just a free particle Hamiltonian with the following equations of motions. And we do the following reduction. We consider the extended space. We take our phase space, T tangent bundle to GLN, to the algebra GLN, and we take a direct product with the coadjoint orbit in GLN, and do just a Marsden-Weinstein reduction by the group action, which acts the same on the phase space and by adjoint action on the orbit. And the symplectic form on this space is just an symplectic form we already introduced, and the constant Kirillov-Suryev for the coadjoint orbit. So generally, what we obtain that dimension of the reduced phase space is equal to 2n, which is Darboux coordinates, plus we have some function depends on the dimension of the orbit. Generally, this is dimension of the orbit minus the dimension of the stabilizer for this orbit. What are the Calogero-Moser systems? The Calogero-Moser systems may be viewed as the systems which reduced space dimension is equals to which reduced space dimension equals to 2n. And how to obtain it? We should choose a non-trivial orbit of the minimal dimension. And these orbits are called Calogero-Moser space and can be obtained by the following relations. So we take a moment map, our commutator, and it equals to rank 1 matrix plus identity matrix. Generally, it may be interpreted by the following things. So if we will consider our phase space here, just schematically this M, and we consider the level set of the moment map, so this is a Calogero-Moser space. Then we take any point from this Calogero-Moser space and we just follow the orbit of the group action here. And then we get to some point on the same level set, but where the dimension is smaller. So generally, this is a point where our matrix Q from the space, our phase space was just a pair of matrices, P and Q. And we get to the point where the Q is diagonal. And then the Hamiltonian we did consider before is just a rational Calogero-Moser system. On the other hand, we can do the same thing. We can continue following the orbit, but now we want to diagonalize not Q, but P. And then we also may get to the same Calogero-Moser space and obtain another point of intersection of our orbit with the level set. And then we will obtain just a free particle system. And it means that at this point, we obtain the Calogero-Moser coordinates. And at this point, we obtain action angle variables for the Calogero-Moser system. So now, what is the Rusinaz duality for in such picture? The Rusinaz duality is the following phenomenon. So we take two Hamiltonians, two free Hamiltonians, trace P square and trace Q square, which are connected by some kind of Fourier transformation. And then we see that they are written on the same phase space. We can take, again, Calogero-Moser space and do the reduction. And for the first Hamiltonian, we obtained that at the green point, we obtained the rational Calogero-Moser, as I explained before, and at the blue point, we obtained the free particle system. But for the second Hamiltonian, we have a different situation. We obtained the free system at green point and the, again, rational Calogero-Moser system at the blue point. So this is kind of duality. So we take two different points from our orbit, which intersects the level set of moment map, and write down two Hamiltonian and do the reduction. So here we obtain that the rational Calogero-Moser system self-dual to itself, because on the other side we obtain the same system but written in different coordinates. So it may be formulated in the following ways, that we have another flow such that the action angle variables for the Calogero-Moser system also is a Calogero-Moser system. So this self-duality, occasionally this self-duality is the consequence of the fact that our initial phase space M, which is just a direct product of the Lie algebras, is symmetric in P and Q. If we will consider a little bit more complicated case, when our phase space is T star to the Lie group, T star to GLN. So again, we identify the space with the direct product of our group and Lie algebra. So now we have a pair of matrices, which and one of these matrices is invertible. Then we consider the natural symplectic form on this space. This is canonical symplectic form. And the same group action, we can consider again two free particle Hamiltonian, which are also connected by the Fourier transformation, and from and reducing at this space from this Hamiltonian. At one point, we obtain hyperbolic or trigonometric Calogero-Moser system, and at the other point, we obtain the free particle system. So it's again action angle variables. And for the other Hamiltonian, we obtain free system at the green point, at the Calogero-Moser coordinates, and we obtain the rational Rusinaz system at the point which corresponds to action angle variables for the Calogero-Moser system. So now we obtain the duality between trigonometric Calogero-Moser and rational Rusinaz system. So we obtain dual system, but not self-dual. This because our phase space is not symmetric anymore. And we may say that this subduality is not a property of the systems, but this is a property of the phase space generally. So, well, you may say that this Hamiltonian is not the same as this one. Okay, we could take the trace of G squared. We will obtain also kind of root in our system, but we will have to do some additional canonical transformations to get to this system. So now what we want to do, we want to expand this scheme to the Painlevé systems. And to do that, I just need to give a brief introduction to the Painlevé equations and the isomorphic deformations. So generally, we can talk about n-hole sphere, but I will talk about only just 4 punctured sphere as our base curve. And then we consider just a G bundle over this curve. And we consider some holomorphic connection on this punctured sphere with the simple poles at the punctures. Due to the Möbius transformation, I can fix 3 points, 0, 1, and infinity, and 1 point will be arbitrary. So the space of such holomorphic connections which have the simple poles at the punctures may be written as follows. And we have one deformation parameter T, which lives on the 3-hole sphere because we don't want to we don't want punctures to collide. So what are the isomorphic deformations? Isomorphic deformations is the same as the consideration of the following connection on the extended phase space when we take the base curve plus cross our space or the deformation space, and we just require the flatness of this connection, and it will be the same as isomorphic deformations. So we obtain some equations, some partial differential equations, and they are actually Hamiltonian with the following Hamiltonian. So we should take a square of our connection of the square of our connection and take a residue at the point T. So this is Hamiltonian for these equations, and the symplectic form is maybe given by the well-known Ilia board, symplectic structure on the space of the connections with the action of the gauge group. And due to Hitch in this situation, we may just consider that our residues of our connection just lives in the in the direct product of the coadjuvant orbits. The symplectic form is given by the constant Kirillov-Suryo on this direct product, and the gauge group action just the diagonal adjoint action on this space. And the moment map is just a sum of the residues, which is quite natural moment map. And this relation may be obtained from the fact that the sum of residues equals to 0. So what are the Painlevé equations? So I will just introduce the Painlevé-6 equation. So the Painlevé-6 equation, the 6th Painlevé equation is just a deformation equations for SO2 connection over 4 punctured Riemann sphere. And these equations can be obtained by the Marsden-Weinstein reduction with respect to the moment map I did introduce before, plus we need to resolve some Casimirs. And the thing is that in this situation, we obtain that the Painlevé equation may be formulated as some Hamiltonian systems with the rational Hamiltonian and the written in the Darboux coordinates. These rational Hamiltonians, they are rational in E and Q, they are quite big and wild, and the natural form, the physical form we want to obtain here is just a kinetic part, which is p squared plus some potential, which depends only on the coordinate q and maybe on the time. So due to Mannion, the Painlevé-6 equation may be now written as a natural Hamiltonian, but not on the previous phase space, but on the elliptic curve, because our potential here is Weierstrass elliptic function. And the time, since we obtained the non-autonomous Hamiltonian system, the time is just a deformation, is a modulus of elliptic curve. So we may view the Painlevé-6 equation as a deformation of model of elliptic curve and some Hamiltonian system on that. And if we will do the autonomization of this system, we will obtain two-particle Inozemtsev systems. It was obtained by Levin and Olshanetsky. And this is kind of the main statement of the Painlevé-Calogero correspondence, that the Painlevé equation may be written as the deformation of the Inozemtsev system. So Painlevé-6 corresponds to elliptic one, Painlevé-5 corresponds to trigonometric one, and Painlevé-4 corresponds to the rational one, and other Painlevé equations are some different degenerations of these systems. So it works for all Painlevé equations, so we can write them into the following form. And the main question is how to obtain multiparticle systems. So to obtain multiparticle systems, we need to consider now not SL2 bundle over four-hole sphere, but now we consider GL2N bundle with the same moduli space of connections. And now we know that AI may be interpreted as the elements of the coadjoint orbits. And to obtain multiparticle system, we put AI to a very special orbit, the orbit which may be written as a tensor product of SL2 with some orbit of the smaller dimension. Due to Kawakami, in this situation, deformation equations may be written as the Hamiltonian systems on T star to GLN, with the Hamiltonians which can be written as traces of some polynomials in Q, E, Q minus 1, and T. These systems are called matrix Painlevé equations. They can be generalized for all p-type equations, so not only for p6, but also for p5, p4, and so on. And as you can see, these Hamiltonians are invariants of the adjoint action of a group. That means that we can do a reduction for these Hamiltonians. And I think, beautiful result by Bertolo, Cafasi, and Rubtsov was that the symplectic reduction of these systems gives us n-particle Painlevé-Calogero systems. So they build this path from some matrix Painlevé equation to multiparticle Painlevé-Calogero systems. On the other hand, we can consider the dual systems reducing from the other point of the orbit, from the other intersection of our orbit with the Calogero-Moser space. And actually, we will obtain some new unknown systems which are dual to the Painlevé-Calogero systems. The main question here is how to obtain isomonodromic form for reduced systems, which can be reformulated in the following form: how to lift reduction to the connections. The answer is the gauge transformation. Since we consider our residues to live in this phase space, so we take some coadjoint orbit and multiply it by SL2, our connection lives in the following space. So we have our phase space, which is T star to G actually, tensor product to SL2, and tensor product to the holomorphic forms on the four-punctured sphere. And we take very special gauge here. It's just a tensor product of some matrix with the identity matrix on of the size 2. So you can see that it acts as and also this gauge is a constant. So we do not have the affine part for the gauge transformation. So it's purely conjugation of our connection. So as you can see, the formula of the gauge means that we act on our phase space as an adjoint action of G, and we act trivially on the SL2. So doing the reduction from the point of view of symplectic reduction, we obtain two different Hamiltonians, reduced one and the dual one. To each of these Hamiltonians, we have different gauges, reduced one and dual one also. And the connection which we obtain after the gauge transformation have the following form. So you can see that they are just a adjoint, so they are just conjugated to the initial connection. So they conjugated to itself. This means that we have the same spectral invariance for these two systems, because spectral curve is gauge invariant, and that's why we call this duality is a spectral duality for these two systems. So now, when we were talking about the Rusnar's duality for the classical systems, we were talking about the action angle dualities. Here, the situation a little bit different, because we have the action duality, because the spectral curve, in a sense, we have a non-autonomous systems, but in a sense, spectral curve fix some action variables. And here we have that we have non-trivial identities between the action variables for reduced system and for dual one. Finally, I want to give you an example, probably our most fresh example, which use the Rusnar systems. Here it is Painlevé's re-equation of type D8. So the Hamiltonian written in the following form, you can see that we have the inverse of the Q matrix. So the natural space for this Hamiltonian is just a space such that determinant of Q is not zero. And occasionally this space is just symplectomorphic to T star to GLN. And using this transformation, which gives us this symplectomorphism plus some transformations, we send this Hamiltonian to the following one. And you can see that here we have combination of two Hamiltonians we considered before. We have a Calogero part, which is P squared, and we have the Rusnar's part, which is G plus G minus 1. So the reduced system is just an trigonometric Painlevé-Calogero system. You can see that we have a diagonal part here, and also we have the potential, which is hyperbolic in the Qi and Qg. This is interaction potential. The dual system takes another form, so we still have this diagonal part, plus we have some part which is just a Rusnar system, which is multiplied by some non-autonomous function, which is exponent of time. So in a sense, in this example, we see that the Painlevé-Rusnar system, they combine together Calogero-Moser one and Rusnar system, and these two systems and their autonomous version were not known before. So, and again, the great thing about this stuff that we have a very different lax operators for these two systems, but we have the same spectral curves and spectral invariants.
Ilia, you have about 3 minutes left.
Yes, I already finished. So thank you for attention. Yeah. And I think I can give some more details on the reduction and our plans during the discussion. Thank you very much. That's all.
Thank you.
Excellent. Thank you. Let us all give a round of applause to Ilia, including emoji round of applause.
Thanks.
Well done. Thank you very much for this talk. Wonderful.